Hi guys, my name is Marzanul Islam and this is my Physics 2212 Lab 3 presentation on magnetic field of a bar magnet. So an introduction, the purpose of our lab is to explore the magnetic field of a bar magnet and we will measure the magnetic field with both a computational model and an experimental model. So a preview of the results, the value for n we got is minus 3.05 and the value for the magnetic dipole is 2.03. So some fundamental principles and assumptions we're going to be making is we're going to be using the Biot-Savart law. We're going to be using the magnetic field of a dipole, which states that the magnetic field exits from the north and enters from the south. And we're going to be using the distance dependence formula of a bar magnet. And an assumption we're going to be making is that the bar magnets acts as a magnetic dipole. So for the procedure, so the system includes the bar magnets and the surrounding includes everything else. And the initial conditions state that the magnetic field produced by the bar magnet. We're going to be placing a bar magnet on a beater stick aligned east-west and position our phone perpendicular. Then we move the phone slowly along a line perpendicular to the meter stick without rotating it, and then we identify the point where the x component of the magnetic field is at a maximum and the y component is the minimum. Then we do the same, but we rotate the phone 90 degrees and find the component where the y is maximum and the x is the minimum. Then the intersection of these two tape placements are where the magnetometer of the phone is located. We will use this to find the off-axis magnetic field. So experimental data, here are the different distances. So we put it at 20, 70, 120, 170, and 220. And then we got the following magnetic fields at those corresponding distances. And then we linearized the data. So we plotted the Lin magnetic field versus the Lin distance. And then we got this graph. And this equation is the equation of the graph. And we will be using it in the following slides. So for the calculation, so we derive this equation from the graph. So ln bx equals to n ln n plus ln k. The y-intercept is ln k, which is equals to minus 14.715. And from that, we can find the value of k to be 4.067 times 10 to the power of negative 7. And then the n is the slope of the graph, which is minus 3.0151, which is approximately minus 3. And then we use the magnetic dipole formula to find the value of mu, which is 2.03. Now for the off-axis experiment and data, I use the same setup as before to find the distance d perpendicular where the net magnetic field is 100 microteslas and record in the spreadsheet. Next, I log the y component of the magnetic field. I place a second ruler perpendicular to the first and move the phone up along it and make sure the sensor is at distance d perpendicular. Then I measure the x, y, z component and then I repeat the process 2 more times to get the 3 values of d and b net. And the spreadsheet will calculate their averages. So here's the distance. All of them are approximately 0.16. This is the magnetic field due to Earth on my current location. And then this is the X component, the Y component. However, the Y component is influenced by the magnetic field to Earth. So I subtracted it and got the corrected formula. And then this is the Z component, and this is the net magnetic field. For the computational model, here we just defined our constants. And then here we entered our magnetic dipole, so which is 2.03. This is the magnetic dipole equation, and these are just creating arrows. So we draw 2 arrows to represent the magnetic field and draw 4 arrows to represent the magnetic field perpendicular to the axis. Here we enter our R value, and then our glow script model gives us the magnitude to be 2.62 e to the negative 5. So the measured value was 6.33 e to the negative 5, and this was a computational model value, and then there was approximately 60% difference. Possible sources of error included the human error in precisely locating the magnetometer and the magnetic interference caused by other objects in the room. So what if I hadn't oriented my experiment to compensate for magnetic north and had instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? Earth's magnetic field would no longer be zero in that direction and would interfere with the magnet's magnetic field, causing us to get inaccurate and skewed measurements. And what if I were to stick two identical magnets together end to end and run the experiment again? How would I expect my measurements to differ? The magnitude of the magnetic fields should approximately double but stay in the same direction. So that's it for my lab. Thank you for your time.